Good afternoon, everybody. It is just about time to start. I see that we have 14 people here. Not quite everybody I'm expecting. I'm just going to wait a couple more minutes to see who else shows up, and then we'll get started. There's one person in the waiting room. I will see if that's who we're expecting. Okay, we're going to go ahead and get started. Good afternoon, everybody. Welcome to Trigonometry. Trigonometry might be familiar for some of you who have been through it before. Others of you might be a little worried because it's been quite a while. One of the things that reassured me most about trigonometry when I was going through my math education was when I walked into one of my first year math courses and we were starting to cover trigonometry. And he said to the entire class, well, here we go. It's trigonometry. Every year I need to refresh myself on this because for some reason it just doesn't stick in my head. And that let me know that not everything works for everybody. Sometimes it takes a little longer to get things than other things. So with that said, hopefully this will go well. I am going to try and pay closer attention to the chat function today so that if you guys are trying to throw questions at me, I'll catch them while I'm going. I'm not the best at that yet, but I'm getting better. Okay, here we go. Where do I want to start with this? Okay, so I'm actually going to stay right on here because I'm going to start by drawing some things right away. Trigonometry. Following along from the lecture notes, it starts off saying that angles may be measured in degrees or radians. And the relationship between degrees and radians can be given by the ratio 180 degrees is related to pi radians. So 180 degrees is in ratio to pi radians. Now, most of the time, we don't bother to write that RAD part, which is just the unit for radians. So a lot of the time, you're just going to see 180 degrees to pi, or however the ratio works out. The reason I wanted to start it off on the whiteboard for this is just to explain where this ratio comes from. Last week, we were doing geometry. We were talking about circles. And we were talking about the circumference of a circle. That area around the outside. Well, if we measure our radius here, and we see that our radius is equal to 1 unit, the formula for the circumference of a circle we learned earlier was 2 pi r. If we say that our radius is equal to 1, then we can say that our circumference is going to be equal to 2 times pi times 1, which is simply 2 pi. So that means that when you go all the way around a circle and end up right back where you started, we've covered 360 degrees, but we've also covered 2 pi. And from there, we can see if we want to get this down just to pi, we'll divide both sides by 2. And we get the relationship shown up here. 180 degrees is equivalent to pi. So that's how that ratio comes around. So that being said, what can we do with this? Well, now we can convert between degrees and radians. So we take our first example. Let's take 45 degrees, okay, and write it in radians. We start off with 180 is in ratio to pi, and we're looking at 45 degrees, and we want to know what it's in relationship to. Excuse me just one second. The waiting room seems to be very, very busy with people, 2 of whom I recognize. There we go. Now we're just doing the ratio work that we were doing before. So I'm going to put this side on top. So I'm going to get 45 over 180 is going to be equal to x over pi. Now we do the same ratio work that we've been doing before. The first thing we're going to start by doing is reducing this fraction. 45 over 180 fortunately reduces to a nice easy number. It comes down to 1 over 4. So now we have 1 over 4. Oops, wrong way around. Is equal to x over pi. We're trying to get x all by itself, so we're going to multiply by pi on both sides. And just for clarity, that looks like that. It's pi over 1. And when we do that, it cancels on this side. And we're left with pi over 4 is equal to x. So 45 degrees is going to be the equivalent to pi over 4. So far, so good. And we'll just do a quick check-in with everybody now that most everybody's here. Everybody is with me? Just waiting for one more quick vote. Okay. Okay, so that lets me know where everybody's at. For those of you who are a little bit lost, thank you. For those of you who are very lost, if you continue to be very lost, we'll try and make a little bit of time one-on-one to get you caught up. Stick with it as best you can, and if there are any specific questions, do let me know. For that question, how did we get that 45 at the end? So, sorry, back to right where we started. We're asked to find 45 degrees in radians. It's basically making sure that we've actually answered the question, because 45 degrees is going to have a ratio in radians, okay, which is what that x is supposed to represent. We're just setting it out like that. Does that help? Great. Okay, let's do another one. But let's now go the other way. I think on the notes I actually forgot to write this out. It's supposed to say write 7 pi over 6 in degrees. So we're going to go the other way now. I'm being given radians, 7 pi over 6. And we want to get these in degrees. We're going to do the same process. Okay? We still remember we set up our first part, 7 pi over 6 is going to be in relationship to x. And this tells us that pi is going to be in relationship to 180 degrees. Please, this is an important part when you're setting up your ratios. This can go either way. this relationship pi to 180 degrees. But always make sure that you're setting up your radians on the same side and your degrees on the same side. Okay? In this case, I'm trying to find degrees, so my x represents degrees, so it has to be on the left-hand side because my 180 degrees is on the left-hand side. Having done that, we can now go ahead and set up the ratio the way we've been doing all the way along. So this is going to look a little bit crowded for a minute. I'm going to show you how we clean it up. Okay, so that's the first side, and that is going to be equivalent to simply x over 180 degrees. I'm going to take a moment and just do a quick little sidebar over here. Okay, and I'm going to take 7 pi over 6 over pi, and I'm going to simplify this a little bit. We want to remember, sorry, I'm going to bring this all the way down. We want to remember that what this is basically saying is 7 pi over 6 divided by pi. So I'm going to write that out like this for a moment. And again, if we remember that pi can be written as pi over 1, when we're dividing fractions, we flip that second fraction and then multiply. So this can become 7 pi over 6 times 1 over pi. And when we do that, those pi's will cancel out, and this simplifies down to simply 7 over 6, which is a much nicer number to deal with. So that's what we're going to do over here. We're going to take this 7 pi over 6 divided by pi, and we're going to reduce that down to 7 over 6, which is then equal to x over 180 degrees. We multiply by 180 on both sides to get rid of that 180 on the bottom. And then that cancels. Then we do a little bit of simplifying here. 6 can go into 180. It goes in 30 times. So now I have 30 times 70, and 30 times 70 is 210. So now I know that 7 pi over 6 in degrees is going to be 210. How was that one for everybody? Just one more vote. There we go. Okay. Okay. Most of you are still with me. A couple of people a little bit lost. Stick with me. And again, if you're completely lost by the end of all this and you didn't get it, be in contact with me so I can spend some time doing some one-on-one help with you. Okay, so that's how we convert between degrees and radians, and that never changes. That's just always the back and forth. We're going to come back to this. Radians is going to come up again, but I have a couple of other things that I need to introduce in terms of vocabulary so that everything makes sense. Okay, next thing we want to talk about are angles. Angles can be drawn inside of geometric shapes, but they can also be drawn on a plane. When we're talking about a plane, we're talking about the thing that looks like this. Okay, simply called the Cartesian plane, or if you don't want to get fancy and you don't always want to say Cartesian plane, you can just say plane, and this is what everybody's talking about. Now, the initial arm of anything that we draw in terms of drawing angles is always drawn across the positive x-axis. So, this direction is always positive. I'm just going to put a little plus down here. This way is always negative. Same thing works on this way. When we're going up, we're always going to the positive. When we're going down, we're going to the negative. That's how these things graph. It's worth noting that in this quadrant, everything is always positive. We're going to be covering this again when we do graphing a little bit later, but for those of you who have been a long way from graphing, I'll just remind you that when we are working on a Cartesian plane like this and we're graphing, our coordinates are always the x-coordinate followed by the y-coordinate. Okay. So in the very first quadrant here, which by the way is called quadrant 1 and is usually represented with a Roman numeral, everything is positive. When we're in the second quadrant, our x values are now negative, but our y values continue to be positive. And this one is quadrant 2. When we move down to quadrant 3, everything is negative in this quadrant. And then we move back over and we're in quadrant 4. And in quadrant 4, we are positive x values and negative y values. And as you can see, what's happening here, as we move around the circle, we're of course moving through the numbers, and we're always moving counterclockwise as we count up. Okay? And the same thing happens when we're measuring our angles. We start from the positive x axis. So in this case, what color do I want to use? Let's go with the fourth color. So when we draw this like this, okay, this is the initial arm. It's along the positive x-axis. And then our terminal arm is always counterclockwise from where we've started. Okay? And when we're using angles, we're often using the Greek letter theta. Just a little sidebar up here. That is theta. So, as long as we're moving clockwise, our angle is always going to be positive. If, for whatever reason, we went counterclockwise, as long as we're moving counterclockwise, we're positive. If, for whatever reason, we need to move clockwise, our angle would be negative. That will come up a couple of times just to make sure that you've covered it. We're going to start off just dealing with the positive angles. So, the quadrant where the terminal arm finishes is the quadrant of the angle. So in this case, we finish in quadrant 2, so the angle we say is in quadrant 2. That's important because we're coming up to an idea simply called reference angles. The reference angle is the measurement between the terminal arm and the x-axis. This one is always your x-axis. So in this case, if I was looking for a reference angle, I need to go back down to the x-axis like that, and that would become the reference angle. Okay? So, I'm going to do this again, but now I'm going to use a specific angle, and we'll just take a quick look at that. I'll bring this up again when we cover the graphing section, but when you're doing a Cartesian plane like this, when you're drawing out a plane, it's really important that you remember to label your axes. Just put an X there and a Y there. Okay, that's just a strong habit to get into. If you do it every time, you don't have to try and remember it. It's just something that you do, and it makes people in mathematics just a little bit happier to know which axes that we're working with. So, say we have an angle. We start with our initial arm here, of course, and our terminal arm happens to come out over here. And somebody's gone and measured the angle for us, and they assure us that the angle is 240 degrees. 240 degrees ends up in the third quadrant, and it's very large. We want to find out what the reference angle is. Remembering that the reference angle is always taking us to the x-axis. Here's our x-axis, so we're going to come back here, and we're just going to look at this part of the angle for our reference angle. How do we get to a reference angle? You're dealing with 180 degrees. So here we go. We've dealt with the first 180 degrees. Sorry, let me mark that to be clear. Our first 180 degrees covers this much. So out of our 240, we don't need 180 of it. So we can say that that's our 240 degrees. I'm going to keep this color-coded. We're going to take away the 180 degrees, and that leaves us with a reference angle of 60 degrees. I'm going to do another one of those just so that it's clear what you're subtracting from what in order to get your reference angle. Wow, that was terrible. Let's try that again. Okay, so this time we're going to start here as always, but we're going to end over here. So we've gone all the way around, and we have it on good authority that we're at 330 degrees. Again, we want to find that reference angle part. So we're coming from the x-axis, which means we're looking for that part. Now, in this case, we don't necessarily need to use 180 because we're in fact much closer to getting all the way back around, which is 360 degrees. So, if I take note that this whole thing, I'll go on the outside here, like that, is 360 degrees. I can take 360 degrees, I can subtract the 330 degrees that we started with, and it turns out that my reference angle in this case is going to be 30 degrees. And if somebody was asking, we're in quadrant 4. Is that better? For those who was asking me to focus the camera. James, is that better? Great. Okay. Continuing on with this same idea of angles on the plane, we're going to talk about the idea of coterminal angles. Coterminal angles is a funny little idea that explores what happens if you happen to be going around the circle more than once. So there we have our nice plane. I'm going to do this one in green this time. I'm going to have one angle that does this, and then it just comes out and does that. And I'm going to say that that's 10 degrees. I'm going to get another angle, and it's going to start at the same place. I'm drawing it like that just so that you can see that they both have the same initial arm. But then it's going to go out and around, and we're going to go through once, which is 360 degrees. we're going to go through twice, which is 720 degrees, and then just a little bit more, and I'm going to end up at 730 degrees. And we can see that when we do that, we end up at the same place. As our 10 degrees. Because we're simply going around the circle twice, plus that initial 10 degrees. And every time you go around a circle, you get right back to 0 again. It's sort of like counting around on a clock. So if we see something that looks like 730 degrees, and we want to know what it is coterminal to that is less than 360 degrees, we simply keep subtracting those 360 degree numbers until we get something small enough. So to make that super clear, 730 minus 360 gets me 370 degrees, and then I'll take my 370, I'll subtract 360, and that gets me my 10 degrees, and that's how I know that they are coterminal. Okay, let's take a look at another one just really quickly. We'll do this one without a picture, and we'll see if we can just do it by the numbers. So, say we have the angles 120 degrees and negative 50 degrees. Are these coterminal? Well, dealing with the 150 or the negative at 50 rather, is a little bit difficult. So one of the things that we can do that's slightly different rather than trying to add and subtract amounts of 360 is we can simply say, okay, do these have 180 degrees in them anywhere? So let's subtract these numbers. 120 minus negative 50, which is the same as 120 plus 50, which gets us 170 degrees. 170 degrees is not a multiple of 360. Which means we haven't gone all the way around the circle. And if we haven't gone all the way around the circle, we cannot be coterminal. Well, let's see if I can actually write that today. Okay, let's do another example. This time we're actually going to find a coterminal angle as opposed to trying to determine if two are coterminal. So this is an example from the notes. We want to find the smallest positive coterminal angle to 890 degrees. So we take our 890. Well, we're just going to start by subtracting 360 degrees, which gives us 530 degrees. We take that same 530, we do it again. We're going to subtract 360 degrees. And when we do that, we get 170 degrees. Now, 170 degrees is smaller than 360. So that's the number we want. And we can say 170 degrees is coterminal with 890 degrees. Okay, and with that, we finished off introducing a whole bunch of terminology around angles on the plane. So I suppose it's time to actually get into the triangle part of the trigonometry. Right angle triangles, right angle trigonometry. Oh, sorry. Bunch of questions on coterminal first. Does one of the angles need to be over 360 degrees for them to be coterminal? It's not that one of them needs to be over 360 degrees, but there needs to be a difference between the angles of at least 360 degrees in order for it to work. How can I show you that? Sorry, before we go on to this, let me just answer a couple of these questions. So let's say that we had an angle at 200 degrees, and I had another angle at negative 160 degrees. How could I tell if these two angles were coterminal? Neither of them is over 360 degrees, and yet they are ultimately coterminal, because if I put them together, if I subtract them from one another, 200 minus 160, which becomes 200 plus 160, and that gets me 360 degrees. Okay, which means that they actually end up at exactly the same place. If I do a quick little picture of what that would look like, there's my X, there's my Y. I'm going to get one of these that does that. Okay, but then my other one does that. And because the angles altogether make up 360 degrees, we can say that they are coterminal. So it's not that they necessarily need to have one that's over 360 degrees, but you need to have at least, as a bare minimum, 360 degrees between them. Great. So in this case, yes, one of them is positive and the other one is negative. It's not always the case, but that is, I wanted to use that one as sort of as a really clear example of how that works. As for the other question, does one of the, which part is the coterminal angle? It's not that, it's the part where they, so the question is, which part is the coterminal? Right here where they meet, that place where they form an angle together, that's the coterminal part. Right there where they meet. Okay. Okay. If we have more time at the end, I'll take more questions on that. I want to keep moving on this because I think there are also going to be some questions in this part. Right angle triangles, right angle trig. We've actually already started dealing with right angle trigonometry. We started, and we've seen it because we've done this a couple of times. We've looked at the Pythagorean theorem. where we have a squared plus b squared equals c squared. And we saw that that only works when we have right-angled triangles. That side is your C, and the other two are going to be A and B. Well, as long as our triangles continue to have those right angles, we can also do a whole bunch of other things. And we're going to start by just starting to label this triangle. So let's say that we have some angle in here. This angle is theta. We introduced that theta symbol a little bit earlier. Well, if my angle is here, this side is always and forever your hypotenuse. C is always your hypotenuse. Sorry, I just realized what I did up there. That should be equals. There we go. Your other two, we labeled depending on where the angle is. The side farthest from your angle that is not your hypotenuse is called the opposite. The side that is right next to your angle that is not the hypotenuse is called the adjacent. And we usually just abbreviate these by the first three letters, which is why I just wrote down HYP for hypotenuse. But I should spell that out for those of you who haven't seen it before. Hypotenuse. But for the most part, we're just going to use the first three letters to represent this. So back to the triangle. In right-angled triangles, whenever you have an angle that you've measured or that you're trying to identify, we can recognize certain relationships that show up over and over and over again. And I'm going to write this down, and then I'm going to explain it. SOHCAHTOA is how that is pronounced, and it is mnemonic, and it helps us remember all of the pieces of our trigonometric functions in right-angled triangles. So, what does this mean? It means this. Sine theta is equal to opposite over hypotenuse. So the S, the O, and the H are dealing with the S, the O, and the H there. The next part, and I'm going to just use the abbreviations for now, cosine of theta is going to be equal to the adjacent over the hypotenuse. So CAH goes with CAH. And then finally, tangent of theta is equal to the opposite over the adjacent. So I want to pause here just for a moment. Sine, cosine, and tangent are relationships, two angles, and they are these things. So when people, if you're questioning, well, what is sine? This is sine. The sine of the angle is equal to the opposite over the hypotenuse. The cosine of an angle is equal to the adjacent over the hypotenuse. The tangent of an angle is equal to the opposite over the adjacent. So when we're looking at it in this case, opposite over hypotenuse is going to be whatever the length of B is over the length of C. For the cosine of theta, it's going to be the adjacent over the hypotenuse, so that would be A over C. And then for tangent, it's going to be the opposite over the adjacent, so that would be B over A. And whatever those numbers turn out to be, that's what the function is. The sine of theta will be whatever the numbers B over C turn out to be. So, let's take a look at what we can do with a thing like that. I'm going to leave this up here, and I'm just going to squeeze the first example in on this so that we can have all of this to refer to as we're doing the question. So we have a triangle, and it's a right angle triangle with an angle of theta. And it's going to look something like this. There's our right angle, and it has an angle theta, which I'm just going to put in here like that. Okay? And we're being told that the cosine of theta is equal to 3 over 7. We've been using green already, so let's use blue to make this clear. So the cosine of theta is equal to 3 over 7. Now, I know that the cosine of theta is equal to the adjacent over the hypotenuse, and I have two numbers here, so I can immediately tell myself, okay, that means the 3 must go here because that's the adjacent side to the angle, and the 7 must go there because that's the hypotenuse. Now that I've got that, I can go ahead and I can use our Pythagorean theorem to figure out what my third side is going to be, which I'm going to label just for consistency's sake. I'm going to call it B. So I know now that B squared plus 3 squared must be equal to 7 squared. So B squared plus 9 equals 21. We subtract 9 from both sides. Why did I say 21? Sorry. 49. That's better. 7 times 7 is 49. 49 minus 9. B squared is equal to 40. We take the square root, and B is equal to the square root of 40. And I'm just going to leave it as the square root of 40 because turning it into a decimal makes it an unwieldy number. So we'll just hold on to it like that for now. So now we know that this, our B, is equal to the square root of 40. So now we have our opposite side as well. Because we now have our opposite, we can fill in the rest of our trig functions if we need to, and I believe I've done so in the notes. Rather than trying to squeeze them messily on here, I will just draw your attention to the notes that sine is going to be equal to root 40 over 7, and tangent theta will equal root 40 over 3. Let's take a look at another one really, really quickly. Do I have, sorry, did I have another? Oh, no, we're moving into special triangles. Ah, good, special triangles. Just before I move into special triangles, does everybody want to see another example of this, or is everybody okay? Just do a quick poll. Pretty close to 50-50. I will do another one out really, really quickly, just so that people can see how it goes. Keeping this information here. So, something comes along, and we're being told that the tangent of theta on some triangle is equal to, let's go with 6 over 8. With that information, we're going to draw a triangle. It doesn't matter where we put theta, so I'm going to put theta in this corner. Tangent is opposite over adjacent, so the opposite has to be there, the adjacent has to be there because of where our angle is. With that, we can now go ahead and figure out our third side from our formula. So 6 squared plus 8 squared will get us c squared. Remember that c. So 36 plus 64 gets us c squared. 36 plus 64 is 100. We take the square root of both. We find out that c is equal to 10. Now that we know that our hypotenuse is equal to 10, we can fill out the rest of our trig functions as needed. Okay, let's talk about special triangles. First thing I want to mention is I am going to provide these special triangles on the test for you, so if you're worried about trying to remember these triangles, you're not quite sure how to represent them on your own reference sheet, they will be on the test, but I want you to see how to use them. And it's going to be going through basically another couple of examples like this. And you'll see what we do with them. Okay. There are two special triangles that get used in trigonometry. The first triangle has got angles of 30 degrees, 60 degrees, and 90. So it's sometimes referred to as the 30-60 or 30-60-90 triangle. The other triangle has angles of 45 degrees at either corner. So it's sometimes called the 45-90 or simply the 45-degree triangle. And these triangles have sort of idealized forms that we use in order to represent certain regular angles that come up at quite regular basis. So 30 degrees, 45 degrees, and 60 degrees come up quite often. So they made up some triangles in order to have the exact measurements for these triangles. And this is how it works out. In a 30-60-90 triangle, we have sides 1, root 3, and a hypotenuse of 2. The reason we do this, 1 squared plus root 3 squared is equal to 2 squared. 1 squared is 1. 1 times 1 equals 1. Root 3 squared is 3, and 2 squared, of course, is 4. So that's how that relationship comes out. And it allows us to do things. So for example, I can then say that the sine of 30 degrees, I'm just going to write this up over here so we can refer to it. Sine is opposite over hypotenuse. There's my 30 degrees. There's my opposite. There's my hypotenuse. So the sine of 30 degrees is 1 over 2. The cosine of 30 degrees. Cosine is adjacent over hypotenuse. There's my adjacent. There's my hypotenuse. So I end up with root 3 over 2. And just to finish off the set, if I then do tangent of 30 degrees, again, that's going to be opposite over adjacent, which says 1 over root 3. For reasons we're going to get into later, this actually gets represented with the radical gone from the bottom and moved up top. So it often gets represented as, in fact, root 3 over 3. It's exactly equivalent to 1 over root 3, but for reasons of convention, They prefer it if we don't put the radical on the bottom. And we'll talk about that more when we deal with radicals. If you forget between now and then and end up using 1 over root 3, I will not penalize you. It is ultimately the same thing. We can do the same thing with our 45-degree triangle. So if I wanted the sine of 45 degrees, the sine is still opposite over hypotenuse. Well, there's my opposite. No matter which way I go, my opposite is going to be 1, and my hypotenuse ends up being root 2. And we run into this exact same problem where we have this radical on the bottom. And this prefers to be represented as root 2 over 2. I'm just going to switch screens for a moment here. Shortly before class, I put up a new resource on the course website that does all of this for you. And I just wanted to share that with you for a moment right now. And it looks like this. And this is a wonderful thing. What we were doing earlier in terms of converting our degrees to our radians, this table then does nicely for us for our most common things. And then it goes on to show off all of the regular things that we were just doing with these special triangles over here. So you can see if we have a 30-degree triangle, our sine is going to be 1 over 2. Oh, look, we calculated the exact same thing. Our cosine would be root 3 over 2. Oh, look, that's what we did. And then our tangent would be root 3 over 3. Again, the exact same thing that we did. Don't worry about these functions down here. We won't be using these particularly. They will come up later in your mathematical education. But all they are is the taking these functions, your sine, cosine, and tangent, and turning them on their head. So if you take sine and turn it on its head, you'll get cosecant. That's what that stands for, cosecant. If you take cosine and turn it on its head, you get secant. And if you take tangent and turn it on its head, you get cotangent. As I say, these are not necessary for our course. This is a nice reference sheet to use in the future. We will only be using these ones. So what this chart does is it takes you through all of the most regular ones up to 180 degrees. And then, of course, if we get coterminal arms in 270 and 360, we're going to get to a place where I show you how to work with all of this. It looks very overwhelming when you first look at it in a big chart like this, but just a reminder, this is simply all of the possibilities that you can pull out of those special triangles, and somebody's just done the work for you already. When you get used to referencing this, it looks much less intimidating. It's just a matter of looking things up. If you want a copy of this, it is on the website and you can download it. I just put it up a short time ago. If you don't want to use this because it just looks like it's too many numbers all at once, you can work all of these things out for yourself using the reference triangles. Okay. Oh, I'm still a little blurry up there, aren't I? That's a little better. Okay, let's do an example with all of this so that we can... Oh, sorry, no, there's one other note I need to make first, and it has to do with calculators. A lot of trig work ends up being done on calculators a lot of the time. So there's something that I just wanted to point out to everybody. Let's see if I can get that in focus. No, that doesn't want to focus. Let me see if I can bring it a little bit closer. Okay, so this is not ideal. What I wanted to point out, sine, cosine, and tangent, these are all buttons on your calculator. You want to be careful when you're dealing with these things. Watch this button that says degrees and radians. You'll have one somewhere on your calculator. And you want to be very careful to make sure that you're in degrees. What you can't see on here because the glare is too much is up in the top left-hand corner. It says DEG. You want to make sure that your calculator is in the mode that says DEG because that stands for degrees, which means that what you're ultimately calculating are the degrees of your calculator. If your calculator says RAD, that means that you're calculating radians. And we aren't asking for our answer in radians at this point in time, at least not in the way that the calculator is going to produce. When we're dealing with radians, we're going to be dealing with those fractions that you saw earlier, 7 pi over 6, for example. So you won't need it on your calculator. When we're going to calculator work, please make sure your calculator is in degrees. Okay. Let's go to an example. I'm going to leave that SOHCAHTOA up there. I'm going to try and leave it visible so everybody can see it. There we go. A balloon is attached to a string measuring 10 meters. The angle the string makes with the ground, the angle of elevation, is 17 degrees. So we draw a picture of that. We've got some balloon up here, and it's on a string. And it's making an angle with the ground of 17 degrees. How high up is the balloon? So we want to know, if we just made a 90-degree angle like that, what is the height? Which I'm just going to represent by the letter H in this case. This is our string, and we're being told that it's 10 meters long. And there's our balloon. So what is the height? Here's how we use trigonometry to figure this out. We always ask ourselves, what do we have and what do we need? So what we have in this case is our hypotenuse. Because we have our hypotenuse, we immediately know that we're down to using either sine or cosine because only sine and cosine use hypotenuse. Tangent does not. So tangent is out. If we were to use sine, we would have to be finding the opposite side, and if we're using cosine, we'd be finding the adjacent side. Taking a look at our diagram, the side that we're trying to find is the farthest away from our angle. Therefore, we're using the opposite side. Hypotenuse and opposite means sine. So we're going to know that the sine of 17 degrees is going to be equal to the opposite, which we're representing by the letter H, over the hypotenuse, which in this case is 10 degrees. Where do we go from here? Well, this is where the calculator part comes in. Sine of 17 degrees is simply something that you end up finding on your calculator. Depending on the calculator, and it may take you a little bit of playing with this, you're either going to hit the button sine and then punch in 17 degrees, or you're going to hit 17 and then punch in sine. I don't know which one it's going to be for your calculators, so try them both ways, but with the number that you should end up with is a very long decimal, the first 4 digits of which are going to be 2, 9, 2, 3. Sorry, thank you for that question. That shouldn't be 10 degrees. That should just be 10, and it comes from the 10 meters. Yes, I meant meters. Thank you for that. So the sine of 17 degrees is, sorry, and I should actually make that when we look at the whole long number, it rounds to 2924 because the 7 comes after the 3 if you're looking at your calculator. So I'm going to go with the properly rounded number. And that's still going to be H over 10. We want to get that height all on its own, so we're going to multiply by 10 on both sides. And when we do that, we end up with and I'm just going to go to 2 decimal places in this case, 2.92. So our height, in this case, is going to be 2.92 meters. Let's do another quick example. We have a wall, and somebody's come along and they've leaned a ladder up against that wall. And we happen to know that the length of the ladder is 12 meters. But we want to know how high up on the wall it has actually gotten to. So again, we're looking at the height. We don't have any way of determining the angle, but we have taken a look at it, and we've managed to measure the fact that our distance here is 6 meters. And we still want to know the height. So again, we don't know our angle. In this case, we're just going to put a theta in. And because we're in the trig section, we have all sorts of questions about, well, how can we go about figuring out that angle to get all of this? And this is one of those places where I'll say, okay, take note, if you've got two sides and you're simply trying to figure out the third side, you can go back to this formula. Okay, so when we do that, we can say, okay, that means that my h squared and my 6 squared, when they come together, should give me my 12 squared. And then, of course, we've been through this one before. 6 squared is 36. 12 squared is 144. Subtract 36 from both sides, which gets me 108. And whatever the square root of 108 is will be our height. But as long as we're here, somebody's come along and they've said, well, what is that angle after all? Sorry, I've got a question from the previous question. Oh, the 2.92 came from, really quickly, just going back to the last question and answering a question. We had 2.924, and we multiplied it by 10. Which gave us 2.924, which I just rounded off to 2.92. The 0.2924 was what happened when we punched sine of 17 into our calculator. Good. You're very welcome. Back to this question. Somebody comes along and said, okay, but what is that angle? You've got all this other information about the triangle. How do you find that angle? Well, now we have all kinds of ways to find that angle, but sticking with the 12 and the 6 for a moment, we'll simply remember to identify what we have. That's the adjacent side. Wow, just not doing well here. One more time. A, D, J, that's our adjacent side. Our 12 meters is our hypotenuse. When we have adjacent and hypotenuse, that tells us that we're dealing with cosine. So we can ask ourselves, I want the cosine of theta, and I know that it's going to be equal to the adjacent over the hypotenuse. I can reduce that and make my life easy, so the cosine of theta will be equal to 1 over 2. When I look at that, 1 over 2 should immediately ring a bell in terms of one of my special triangles. Dun, dun, dun. I'm just going to bring this back. So we take a look at that 30, 60, 90 triangle. If 1 is my opposite, or sorry, is my adjacent, and 2 is my hypotenuse, then I know that I'm looking at 60 degrees as my angle. So I can go ahead and I can say that theta is equal to 60 degrees. Okay, let's take a look at using this same sort of thing, but we're going to look at it back where we started, where we're back on the plane. Okay, so x, y. We've got some angle theta. Okay. And we've got a point on our terminal arm, and we're just going to call those points x, y for the moment, remembering that's what we started with. And we're also going to say, well, what does this have to do with triangles? Well, we're going to remember we also have a reference angle somewhere in here, and it goes like that. Now, why is this point x, y? Well, if I go out this far, I'm going to go out whatever this is. That's going to be my x value. And then whatever that is, that's going to be my y value. And then if this, of course, I'm just, for the time being, I'm going to call this length from here to the point r, like it's the radius of a circle. Okay. From that, we know the following. Our radius is going to be equal to the square root of x squared plus y squared. And this is just a rearrangement of that sort of formula. But the other thing we can then identify is we can see how our trig functions, our three basic trig functions, define out from all of this. So this means that the sine of theta in this case is going to be y over r, okay, opposite over hypotenuse. The cosine of theta then must be x over r, so again we're going to get the adjacent over the hypotenuse, which then leaves us the tangent, which will be y over x, which is to say opposite over adjacent. Let's do an example that uses all of this. Suppose that we've got the terminal arm of an angle, theta, that passes through the point -3, -2. So let's just take a moment. We're going to redraw this. We're on some plane. There's our x. There's our y. We're being given the point -3, -2. So if we go back to -3, go down to -2, we'll call the point approximately there. There's our initial arm. There's our terminal arm. And there's our point, -3, -2. In order to find that length, we go back to the rearrangement that I had given you earlier. I'm going to take a moment. I'm just going to show you how that rearrangement comes about. I'm just going to throw down R on there to let you know that we're going to that point. Drawing from our Pythagorean theorem, I'm going to get -3 squared plus -2 squared. Let's stick these in brackets for clarity. And that should get us to our r squared. I don't want r squared in the end. I just want r, which means what I've done is I've simply taken the square root on both sides. And drawing this out in detail just for a moment, it would look like that. I can then go ahead and do that. And then we find out that r is simply equal to the square root of 13. Okay, so let's say that we want to find the cosine of this angle. What is the cosine of theta? Cosine, we remember, is going to be adjacent over hypotenuse. The other way that we were looking at cosine is also to think of it as x over r. Our x in this case is -3. Our r we determined was the square root of 13. So using these things, we can say that the cosine of theta is going to be equal to the negative of 3 over root 13. How are we doing for time here? We're starting to get a little bit tight. I have a couple of more examples that I want to go through, and then I have one other piece of content to show you. And then I'll be free to take questions on any and all of this. So, my apologies, everyone. My internet got dropped for a moment there. I'm back now. Okay, sorry. As I was starting to say, I've got a couple more examples I want to get through, and then one more piece of content, and hopefully my internet will not kick out again. I don't know why that happened. and then I will be able to take questions that I haven't been able to answer as we go. So, we're being told that some angle theta is in quadrant 2. Okay? And we're being told that the sine of this theta is equal to 1/5. What is the cosine of theta? Remembering that the sine of theta is going to be y over r, we now know that y will be equal to 1 and that r is equal to 5. Since we're in quadrant 2, the other thing that we know is that x must be negative. Let me just draw that out really quickly for those of you who are not following that. Remembering that that's 1, that's 2, that's 3, and that's 4. In this quadrant, x is negative and y is positive, so our x value has to be a negative number. So we can just take a note that x is negative. We can then stop and we can use the Pythagorean theorem really, really quickly. We don't even have to start drawing too many angles. So we know that what we're looking for in this case r is going to be equal to the square root of x squared plus y squared. We know what r is. It's 5. We know what y is. It's 1. So we're just trying to figure out what x squared is. So going backwards really quickly, I'm just going to call that x squared plus 1. In order to get rid of the square root sign, I'm going to square the whole thing. But whatever we do to one side of an equation, we must do to the other. So 25 is going to be equal to x squared plus 1. We'll subtract 1 from both sides. So x squared is equal to 24, which means x is going to be equal to the square root of 24. We also already identified that x is negative, so we're going to make that a negative. Okay. We still need to remember to answer the original question. What is the cosine of theta? Cosine is adjacent over hypotenuse, in this case x over r. So we can say the cosine of theta will be the negative of root 24 over 5. I'll just put this up here also. Okay, one quick example that I want to pull up, and it will start to explain why on the trig table that I was showing you earlier, there's a whole bunch of places where you just get a dashed line. Just show those for a quick second so you know what I'm talking about. And see some places we get this dashed line that shows up. Okay. So let's take a look at this. This is for 90 degrees and tangent. Why does the tangent of 90 degrees have a dashed line? Well, let's do that and find out what's going on. So, tangent of 90 degrees. to draw a quick picture here so that we can see what it is we're looking at. There's our initial arm. Well, if we're going to make 90 degrees, we're obviously going to be going straight up and down like that. If we do that, at some point, we're passing through a point on here, which is the point 0, 1. The reason we call it 0 is because we're right on that line. X is always 0 right on that line. And no matter how far we go up, at some point, we're going to have to pass through the number 1. So we would call our point there 0, 1. Tangent is equal to your opposite over your over your adjacent. Okay. Well, when we take a look at that, opposite in this case is going to be our 1. Okay. The adjacent, though, if we're just going straight up, we have no length, so we actually have a length of 0. So we can say that our opposite in this case is equal to 1, but our adjacent is equal to 0. So when we take a look at tan theta with those numbers in mind, we end up with 1 over 0, which in mathematics we say is undefined, which is a very fancy way of just saying, no, don't do it. You are not allowed to divide by 0. So when we look at the tangent of 90 degrees, we end up dividing by 0, and we're not going to do that, which is why in all sorts of places you'll see that there's that dashed line. Wherever you see that dashed line on that chart, that's where we've tried to divide by 0, and that's simply not allowed. Okay, one last thing to talk about. What happens if we are not dealing with a 90-degree triangle? Well, there's a couple of things, but you're only responsible for one of them, so we're going to talk about it. Non-right angle triangles. In non-right angle triangles, we're going to use a thing called sine law. The nice thing about sine law is that it uses ratios, which we're already quite familiar with using. And the ratio says that the sine of any angle A and it is in ratio to the sine of B, which is in the ratio to the sine of C, and it is going to be equivalent to the ratio of the sides A, B, and C. We have a triangle. There's the capital C, there's the lowercase c, capital A, lowercase a, capital B, lowercase b. So when we take these things and we notice that they're going to be equivalent, it means that we can write out very nicely a relationship that looks like this. Sine A over A will be equivalent to the sine of B over B, which is equivalent to the sine of C over C. And we can go ahead and use this relationship anywhere where we have a side and its angle opposite, and then one other piece of information on the triangle. Which is to say, as long as you can form one complete fraction like that, and then have any other piece of information in this set of information, you will be able to solve this. And let me show you an example of that. So I'm going to keep this relationship up. I'm going to draw a different triangle, though, so we can see how it works out. So here we go. Here's some triangle. And we've got degrees of 15, 115. If you've got two angles, you've always got the third. So we'll call that 50. And then we're being given another side, and we're being told that that side is 3 centimeters. Well, here then I have an angle and its side opposite, which means that I can go ahead and write that out. I know that the sine of 15 is going to go over 3. Just for clarity, we're going to label the other sides. I'm going to call this side B and this side C. It doesn't matter which way you label it. It all works out. We're just doing it this way so that we have some labels. We'll solve for B first. In order to solve for B, it means I'm going to be using the sine of 50, simply because this angle must relate to that side. And now we're all set up, and the only thing we need to do now is solve for B. So, this involves a whole bunch of rearranging. I'm going to go through it in some fairly minute detail, just so that for those people who aren't as familiar with how the algebra works, you can see it all. Everybody hold on to that mental picture in your mind. I'm going to need the space. Sine of 15 over the sine of 50. I'm going to keep things in the form of sine 15 and sine 50 while I rearrange it for a moment, and then I'm going to turn those into numbers from the calculator as the last step. So the first thing I do is, to make my life easier, I'm going to flip these things over. So I'm going to get 3 over the sine of 15 is going to be equal to B over the sine of 50. I'm trying to get B on its own. It's being divided by the sine of 50, so I'm going to multiply by the sine of 50 on both sides. And that makes that go away. So then what I am left with, I have the sine of 50 times 3 divided by the sine of 15, and whatever that turns out to be is going to be my letter B. When I do this, the sine of 50 comes out to approximately 0.766. 3 is still 3. It's a number already, so we can just leave it alone like that. And then the sine of 15 is going to be approximately 0.2588. Then we put that into the calculator. We actually multiply these things all out. So 766 times 0.766, sorry, times 3 divided by 0.2588. And we end up with a number that says that it's 8.87944, and the numbers keep going on forever. We're going to approximately round this down to 8.88. And that's a satisfactory answer. having done that, we can do the same thing now for the sine of c. Just give everybody a chance to finish copying that down. But I'm just going to go right back to this step. And it's all going to work out approximately the same way, although, of course, with different numbers. So I'm going to keep my initial sine of 15 over 3, but now I want the sine of c, which we decided was 115 over c. Again, to make my life easier, I flip things upside down. So I'll get 3 over sine of 15 is equal to c over the sine out of 115. Again, I'm going to multiply by the sine of 115 on both sides to make that cancel out. And I will have sine of 115 times 3 divided by the sine of 15, and that's going to be equal to c. Plugging all of these things into a calculator, the sine of 115 is going to be 0.9063 approximately. 3 stays as it is. We already knew what the sine of 15 was. We can use that same number, 0.2588. We plug all of this into a calculator, 0.9063 times 3 divided by 0.2588. And C comes out to 10.505795, and it goes on and on. So again, we're just going to round this down, and I'm going to get 10.51. So it's important to note that except for the addition of using the sign button on your calculator with all of this, this is still working out the same way as it was in previous weeks as we were working with ratios. Okay, the timing on that worked out fairly well. I have some time to go through some problems that I can pick from the homework, or if there are some burning questions from previous week's homework that people would like to throw at me right now, or questions from this lecture that you would like for me to clarify first, go ahead and start throwing those at me. Otherwise, I'm going to just pull up some questions from the homework, and we'll do a few of those before the end of the lecture. Okay, let's do, I'm seeing some requests. Sorry, 1 second. I'm getting, okay, so we have some requests for things before we get into the geometry. I'm being asked to take a look at the fractions. Okay, I got to pull up my fractions notes. Hold on 1 second. And then I also have a question from the geometry, so I'll pull that one up at the same time. Okay, so this is again a ratio question that sorry, let me come back here and share this so people can see what we're looking at first. Is this the example you'd like me to go through one more time, just to be clear? Okay. So we're being given the ratio, 3 to A to 2, which is equivalent B to 9 to 8. Okay, so here we've got this all set up. This is actually a good and appropriate one because this is the exact same process as we just went through for sine law. We have the sets of ratios, and we then turn these into equivalent fractions. So I'm going to take this, and it's going to become the bottom set of this. So I will have 3 over B, which will be equal to A over 9, which will be equal to 2 over 8. And now I can go ahead and I'm going to use the 2 over 8 because it's my complete fraction, and I'm going to use it to solve the other two pieces. So 2 over 8 will be equal to A over 9. I'm trying to get the A all by itself. It's being divided by 9, so I will multiply it by 9 to undo that. Whatever I do to one side of an equation, I must do to the other. So then those cancel. 9 times 2 is 18. The 8 stays where it is. That can reduce these things, both divide by 2, and I end up with 9 over 4. And that's going to solve that A. I can do it again. Oops, let's make sure we get these things in the right place. 2 over 8 will now be equal to 3 over B. The thing I want is on the bottom. Whenever I see the thing that I want on the bottom, I always flip the entire thing to make my life easier. So I end up with 8 over 2 is equal to B over 3. I want B on its own. It's dividing by 3 right now. So I will multiply it by 3. Whatever I do to one side, I do to the other. Those cancel. 3 times 8 is equal to 24. And it's over 2. And of course, 2 goes into 24 evenly, and it reduces to 12. So now that B is equal to 12. So as you can see, except for the setup, it's the exact same process as we went through for sine law. This whole process with ratios is an incredibly useful tool to have in one's toolbox. Okay, well, I'm going to do the fractions request first, and then I'll come back to the geometry one. And I have seen your question, Simona, and I will answer it before we close out for the day. So, just for clarity, Jackie, you're asking fractions 9 and 10. Is that from the homework, or is that from the lecture? From the homework. Okay, so from the fractions homework, questions 9 and 10. Let's take a quick look. So this is decimals to fractions and percentages to fractions, which ultimately ends up being the same process. So that's good. I just want to get this called up so that everybody can see it. So for those of you following along, we're going to express decimals as improper fractions in lowest terms, and then percentages as improper fractions in lowest terms. We'll start with the decimals. The fractions ends up being the exact same process, but with one step added to the beginning of the whole thing. I'm just going to write down a whole bunch of these decimals to start with. I'm just going to do that many for now. So I'm going to do these 4 to start with. In the process, this is a 4, 5. So 0.15. We start off by noting that it has 2 decimal places. Because it has 2 decimal places, I'm going to put it over a 1 followed by 2 zeros. Okay? 2 decimal places, 2 zeros. Once I'm in this position where I have the 15 over 100, I'm going to reduce that to its lowest terms. I note that both 15 and 100 can divide by 5, so that's what I'm going to do. I will divide by 5 on top and on bottom. 15 divided by 5 is 3. 100 divided by 5 is 20. And that's as simple as I can make it. .235 would go through the same process. I have 3 digits that I'm dealing with inside my decimal, so I need 3 zeros on the bottom. Once again, this one ends in a 5, which means I know it will divide by 5, so that's the first step that I'm going to take. Whatever I do to the top, I must also do to the bottom. 235 divided by 5 is, oops, keep my colors straight here, 47. 1,000 divided by 5 is 200. And then there's nothing that divides both 47 and 200, so we're done there. For clarity, we're only counting the digits to the right of the decimal. So when we take a look at something like 3.45, I still only have 2 digits to the right of my decimal. So even though I'm writing 345 on top, I still only want 2 zeros. Once again, we happen to be able to divide by 5, so I'm going to. And when I do that, I end up with 69 on top and 20 on the bottom. There is nothing that divides both 69 and 20 evenly, so I'm done there. Last one, just because this one looks a little bit funny, but nothing is actually changed. We're going to go through the exact same process. .08. The .08 tells me that I have 2 numbers to the right of my decimal, so I'm going over 2 zeros. Now I don't have anything that divides by 5 nicely, so I have to go with something else. These will divide by 2. I'll start with that, and I'll see what I get. 1,008 divided by 2 is 504. 100 divided by 2 is 50. Still even numbers, so I can still divide by 2 top and bottom. When I do that, I get 257 on top, and I get 25 on the bottom, and there is nothing that divides both 257 and 25, so we're done there. Now, the only thing that's different when we go to do this with percentages, let me just write down some percentages here that we're going to deal with, is the one step that we need to do before this, which is turning our percentages into decimals. And again, I'm just going to do these 4 just to make it easy to see what's going on. So I have 3.24%. Okay. Our very first step is always to move this 2 decimal places to the left. We need to turn this into a decimal. There's numbers of ways that you can think about it. One of the ways you can think about it is to say, okay, well, let me divide this. Sorry, I do this in a different color. Let me divide this by 100 to turn it into a decimal. Doing that is the same as saying I need to move this decimal 2 decimal places to the left. And when I do that, I'm going to end up with a number that looks like that. And now I have 1, 2, 3, 4 decimal places, which means I have to go over 1, 2, 3, 4 zeros. I take note that both of these things will divide by 4, so I will do that top and bottom. And when I do that, I end up with 81 over 2,500. And I don't believe there's anything that divides both of those evenly, so we're done there. So as you can see, the only process that we've added is this take your percentage and divide it by 100 step. In other words, take your percentage and move your decimal place 2 spots. And then you're into the decimal and you're following the exact same process as we did from above. I will do a couple more just for clarity. %. We're going to divide that by 100, which is to say we move our decimal place 2 spots, and I end up with 0.85. It has 2 decimal places, so that tells me that I'm dealing with 85 over 100. In this case, it divides by 5, top and bottom, and I'm down to 17 over 20. I'm actually going to stop there. It is the same process, but I want to take a moment and take a look at the geometry questions that I've been asked. Geometry homework questions 17 and 18. Jackie, I hope that was sufficient for you. If not, please let me know and I will send you a couple of more worked examples. From the geometry homework, we're looking at questions 17 and 18. The last 2 questions, yes. Okay, so let me show this to everybody to start. Find the area of the following shape. Give both the exact answer and the approximate answer rounded to 2 decimal places. So, I'm going to start off by drawing this shape. Oops, that was terrible. Okay, So a couple of things to note. We're being told that this length is 2. We've got the double dash, the double dash, the double dash, which means all of those lengths are 2. The other thing that we take note of, this is a quarter of a circle. So whatever we're going to end up dealing with, we're going to be we have to deal with a quarter of a circle in the whole thing. This is asking us for area. So we just remind ourselves of a couple of things. The area of a circle is pi r squared. The area of a triangle is 1/2 base times height. That's a circle. That's a triangle. We'll start with the circle part. We have a radius of 2, so that's going to go in there. We only have a quarter of this circle, so we're going to divide the whole thing by 4. So pi times 2 squared, all divided by 4. This is this area of our circle. I'm just going to put a little sub-circle down there so that we're clear on what's going on. The area of our quarter circle is going to be this. I'm going to just leave things like this for a moment. 2 squared, of course, is 4, and it's over 4. When I do that, I'm left with just pi. So the area of my circle, or of my quarter circle in this case, is just going to be pi. And let's hold on to that just for a moment. Now we move on to the triangle part. Well, we want 1/2 base times height. Our base is the same as that. Go ahead and fill that in with a 2. Our height is also 2. So the area of our triangle is going to be equal to 2 times 2 divided by 2, which is a little bit silly, but that's just how the numbers work out. 2 times 2 is 4, and 4 divided by 2 is 2. So in this case, the area of our triangle is going to be equal to 2. So what do we do to make this whole thing finalized? Well, I've got the area of my quarter circle, the area of my triangle. If I add those things together, that should give me my final area. So that's exactly what I'm going to do. I'm going to go 2 plus pi. That's my exact answer. Remembering that pi is approximately equal to 3.14. I can say that my approximate answer is going to be equal to 5.14. And I have just enough time to squeeze in that last question. But it works basically along the same idea. Oh, sorry, you guys aren't looking at what I'm looking at. So, we're going to do this question now, for those of you who've had problems with this one. We've got some wedge of a circle here. Okay. And we're being told that that's 30 degrees. And that length there, that length there is 2. The trick to this question is remembering that a circle has 360 degrees. Because we've got 360 degrees in a whole circle, but we only have 30 degrees in this little wedge, we can find out what fraction of the circle we actually have. I'm going to put 30 over 360, and then we're going to reduce this. It's a little trick I haven't had a chance to show in case you haven't seen it before. If you have zeros top and bottom, which is to say things that are being multiplied by factors of 10, those parts just go ahead and cancel out. It's like dividing by 10, which leaves me with 3 over 36. Well, 36 divides by 3. So this tells me that I'm left with 1/12 of a circle. That is going to be very important to us. We're being asked for both the area and the circumference. Sorry, not the circumference, the perimeter. But it's going to involve the circumference. Area of a circle, as we just saw from the previous question, is going to be pi r squared. In this case, our r is equal to 2. Okay, and we don't need the entire area. We only need 1/12 of the area, which is to say we're going to divide this by 12. So I can go ahead and I can say that my area will be equal to pi times 2 squared, and the whole thing will then be divided by 12. Just to say pi times 4 divided by 12. Well, 4 goes into 12 very nicely, and I'm left with pi over 3. For clarity, that should be pi over 3 units squared. I don't think we were given a specific unit for this question. No. So we just say units squared as our final answer. So for the perimeter, the first thing that we need to do is we need to calculate that part. Well, that part is going to be 1/12 of the circumference of a circle. So the circumference of a circle, remember, is 2 times pi times radius. Our radius is 2, so the circumference is going to be 2 times pi times 2, which is simply 4 pi. We want 1/12 of that. So we're going to take our 4 over pi and we're going to divide it by 12. Interestingly, it gives us exactly what we had in terms of our area, which is pi over 3, but it's not square units anymore, it's just units. We should note that is not the entire perimeter. What we have calculated with this is just from here to there. In order to find the entire perimeter, we still need to add the wedges part of our pi slice. So we need to add 2 plus 2. So our final answer on the perimeter part is going to be our pi over 3 plus 2 plus 2, which is ultimately going to be 4, and pi over 3. Or if you want to be fancy, we can go with, 13 pi over 3. Okay, I'm taking note of our time. Just really quickly, I'm seeing there might be some people who are wondering how that 13 came about. Remember, that's 3 times 4 plus 1. 3 times 4 plus 1 gets us to our 13 pi over 3. So, Simona, I promised to answer your question right at the end here. This is for anybody and everybody who's planning on taking the test on Thursday. Are we able to have any or all notes for the test on Thursday, or only a reference sheet? I'm requesting that you get it down to a single sheet if you can. The reason I'm requesting that is because if you have lots and lots of notes that you need to flip through, you're going to spend more time running through your notes than actually doing the test part. So as much as you can, if you could keep all of your notes to one sheet of paper, I would appreciate it. If you have to bring in more than one sheet of paper, try and limit it to 2 sheets of paper. But the more that you can keep it to one sheet of paper, the better. Does that answer your question, Simona? Perfect. I will go over that again right at the beginning of class next time, and I will also make sure that we're getting everybody in the right breakout rooms to write the test, and that everybody's downloaded the test properly. I'm going to try and be in the classroom about 15 minutes early to help people get set up for that. If you're a little worried about that and you want to start right at 4 o'clock or 4:30 rather, I should be in the room by 4:15 on Thursday. Okay, I've run a little bit over time. Thank you all for sticking with me. How many questions are on the test? That's a good question. I don't recall. Let me just look at it really quickly. There are 13 questions on the test. And the geometry video should be posted at this point or very close to it. I'm still new to this YouTube thing, so it was uploading and processing through YouTube. The link I've already put up on the website for the geometry stuff. I haven't managed to re-record fractions yet. My apologies. This one, though, is recording, so I should be able to get this one up in a couple of days also. If I'm lucky, it'll even be up tomorrow. Okay, that's everything for today, folks. Thank you very much. I will see you again on Thursday.